Hi folks, this is Murphy. I wanted to create a video to kind of wrap up where we left off, or approximately where we left off, with section 1.3, describing quantitative data with numbers. This includes talking about, wrapping up some of the big ideas with box and whisker plots, including how to create them, how to quantify what an outlier is, go on to talk about standard deviation, and then look at what is considered proper notation for some of the symbols that we're going to be using in this course. Um, just a side note, if you hear any like munching or scratching or sniffing, that's my dog. It's not exactly ASMR material, but it's better than barking, so we're gonna have to deal with it. Um, so some of us, depending on what class you're in, left off last time by talking about a box and whisker plot and how to make it, and we talked about something called a 5-number summary, which is, hang on, these. The 5-number summary is the set of 5 points, essentially the quartiles, that make up each of the 5 significant points in a box and whisker plot. We also said that if I want to quantify what an outlier is, we would need to use the 1.5 IQR rule. That's important to remember. The IQR is the inner quartile range. That's Q3 minus Q1. It's essentially the range of the box, the middle 50% of data. And in this case, Q3 minus Q1 is 27.5. According to the 1.5 IQR rule, I should then multiply that by 1.5. That comes out to 41.25. I've got this all written down on the side. And then I should check with that 1.5 IQR, that 41.25. I should look at the value that is that much more than Q3 and that much less than Q1. So in other words, 15 minus 41.25 brings us somewhere in the negatives, which is well below our minimum, which means we don't have an outlier on the left side of the data. On the right side, if I take that 41.25 and I add it to Q3 though, that gives me 83.75. So what this means is anything that is equal to or greater than 83.75 is an outlier, which means that our maximum value here, that qualifies as being an outlier by the 1.5 IQR rule. So if I were to graph this, one way that I can graph the data using a box and whisker plot is to exclude the outliers, because if I were to extend this whole whisker from Q3 to the maximum, this would indicate a very big spread with the last quarter of the data, which is not strictly accurate. The spread is still pretty big if I go from the 42.5 to the 65, but not nearly as big as if I were to extend to the outlier. So making this a separate point really better demonstrates the idea of spread here. So something worth noting, and I mentioned this in class too, you definitely want to plot the x-axis before you plot the box. We don't want to plot the box with things randomly spaced and then put the x-axis under it, because then things won't be drawn to scale, and we want consistent intervals. In terms of interpreting this, think about what it means that this whisker is a little bit less than half as long as the right whisker, the right 25% of the data. That doesn't mean that there's more data in this whisker than this whisker. They both represent 25% of the data. What it means that this whisker is so short relative to this one is that 25% of data is more condensed. So we can actually look at this 25% and see it ranges from 5 to 15. This is a spread of 10 units, as opposed to this last quartile, which, even if we exclude the outlier, goes from 45 to 65. That's a much bigger spread. It is twice as big as this. So keep in mind what we're looking at, how to interpret it, and basically the fact that we have this box right here tells us that since the right half of the data is so spread out, like the third quarter of the data and the fourth quarter of the data, this pretty much tells us that we have a right skew. And the outlier pretty much is consistent with that as well. So that's box and whisker plots. A big deal in this course, as you can tell by the rainbow font, is standard deviation. So if I want to calculate, or if I want to talk about the spread of a distribution, yes, range is one way, yes, percentiles and quartiles are another way, but what you're going to typically find as a typical measure of spread is the standard deviation. So if I look at this set of, 1, 2, 3, 4, 5, 6, 7, 8, 9, this set of 9 data points, where each one represents the number of pets in a hypothetical household. We could see the center is somewhere between 4 and 5, perhaps. We can get some idea of the spread by looking at the whole thing, like the range is 8. But if I want to talk about what the standard deviation is, remember that the standard deviation by definition is the typical spread from the mean of the data. So if I want to talk about the typical distance of a data point from the mean, I can actually calculate the differences. So remember, x bar is a sample mean, and each xi here is each of the 9 data points. So what I can do is I can actually calculate the difference that each of these points is from the mean, and I end up with each of these values. Like this one data point is -4 units from the mean. I know that's not typically how we talk about distance. That indicates the negative 4 means that it's 4 units below the mean, which I guess happens to be 5, if I were to calculate this data on the side. So seeing as we are talking about distance, it seems weird that we have negative point values here. In fact, we end up with a problem if we look at the negative, or I should say, if we look at the distances in terms of direction, because when I look at this, I end up getting a sum of 0. So it doesn't make sense to say that the standard deviation is 0. In fact, this would happen every single time, because that's kind of part of the definition of a mean and how it's calculated. It's going to work such that the sum of the differences from the mean are going to be 0. So what if I just want to look at their positive values? Well, what I could do, if I want to look at the positive values, some of you may have thought in your head already, like, all right, take the absolute value of this column and then add all of those, and then use that for calculating the standard deviation. Good thought, student, if that's where your brain went. However, and I'm about to dip into a bit of calculus, so some of you may appreciate that. Creating a function that essentially works with absolute values isn't great for calculations. Like I said, if you're a calc student, you probably know why. The absolute value function is not smooth, it's not differentiable, it's not great for calculations. So another way of making sure that every difference that we have and every distance, so to speak, is positive is to not take the absolute value, but to square these values. So what if I take each difference here, each value in this column, and then I square it? I get 16 and 4 and 1 and 1 and 1 again, and then some numbers. We're really squaring it because not only does it ensure that we're talking about the positive distance that each point is from the mean, but it has the added benefit of exaggerating the big differences. So for example, the farthest away from the mean that any given point is 4. These are very much exaggerated by the fact that when I square it, if I square a bigger number, it becomes even bigger by a greater magnitude, right? This sum ends up being 52. And again, if I am talking about the typical or average distance from the mean, and I have 9 data points, I'd want to divide 52 by 9, which makes this minus 1 in here very odd. But we'll talk about this on the next page. What I'm essentially doing is taking the average, air quotes average, distance from the mean. And I know that this has been kind of butchered by the fact that I'm not doing distance in terms of absolute value. I'm squaring things. I'm not dividing by n, the number of data points. I'm dividing by n minus 1. It's all very strange, but trust me, there's good reasons for it. And frankly speaking, this course deals with a lot of concepts where you don't necessarily have to understand how the calculations are derived. We should just be able to understand the general ideas of why things come to be and what they mean when we work with them. In fact, don't try to remember any formula. Don't try to derive this formula on your own. You're going to have a formula sheet, and we're almost never going to have to do this by hand. Actually, you have the Murphy guarantee. You're never going to have to calculate standard deviation by hand, because we're going to talk about good ways to do it in your calculator more quickly. But for now, just know that 6.5 is the variance in this case. It is the average squared deviation. And remember, too, that squared deviation, we could think of that like standard deviation squared. That's what variance is. It's sigma squared. So then if I want the actual standard deviation, I would square root that, and the square root of 6.5 is 2.55. So just to recap, the standard deviation measures the typical distance that a point is from a distribution's mean. So the fact that the SD comes out to like roughly 2.5 in this case is to say that typically the number of pets owned by any given household in this study is going to be 4, roughly plus or minus 2.5 pets. We don't round this up to 3. This is a very specific statistic that we use for calculations, so we don't round it because of context. We keep it as it is. But that's how we would interpret this in the context of the problem. You know, there's 4 pets, or rather 5 pets per household, plus or minus 2.5 on average, or typically. So again, to recap the whole process of finding it, what we've done is we have squared each deviation, where I'm considering these values to be the deviations, the distance from the mean. What we've then done is we have found their average by adding them up and then dividing by, not quite n, but n minus 1. That's why average in air quotes. That grants us the variance, and then when we take the square root of that, we find the standard deviation. We'll talk more about this in the future. But basically, you need to know a couple things. One is that the ingredients involve squaring the differences and then taking the average. And then also what this means in context. It means really more or less plus or minus the mean gives us what we would expect as a typical value in that distribution. So we've talked about some symbols before, like we talked about X bar in the previous page. We also talked about sigma. The ways in which we use each of those things depends on the source of our data. So in other words, I could be looking at a general population, in which case I'd have symbols to represent the population mean and the population standard deviation. But most of the time what we're going to be doing is we're going to be collecting data from a simple random sample of the population. That's actually a vocab term that we're going to define later, simple random sample. But we need a way to distinguish the sample mean from the population mean, and we do so by using different symbols. This is true with the size and the standard deviation as well. I don't know why that bar didn't get fleshed out, but the sample size is lowercase n. The sample standard deviation is lowercase s, and the mean is x bar. If I talk about these things in terms of the population, I either get capital or I start using mu. I guess capital S looks, or sorry, not mu, Greek in general. I guess capital S looks too much like little s. Same thing with capital X looking too much like little x. So instead of big S and big X bar, we use Greek letters instead. So here's the sigma that we were talking about, even though it's lowercase Greek sigma. And then here's mu, pronounced like MU, or like MEW, like the cat. And these are the symbols that are associated with either a population or a sample. We've talked about this, I think, in the summer work videos that you definitely watched, am I right? Where statistic is a value related to a sample, or parameter is a value related to a population. And these right now, like if you don't feel like you have to write this down or try to make sense of it, this is going to come very naturally as the course progresses, because these are symbols that are going to appear very frequently. So I might get on your case about remembering to use x bar instead of mu if you get that backwards. But otherwise, just trust me when I say that this is going to become a thing that will do so much it becomes second nature. The formulas for each of these things. The means. The sample mean is exactly as discussed. It looks more formal than it is. You just add up all the sample values and then divide by the sample size. The sum of all the values divided by the number of values in the sample. Same thing with the population mean, mu, except notice that we have big N to represent the population size. My dog, man, cracking me up. Standard deviation. This is a very complicated way of looking at what we just did on the previous page. Without the square root, it is the variance. It's when we took the sum of the difference columns squared, and then we divided by 9 minus 1 on the previous page. And that was how we got the sample standard deviation, right? That was definitely a sample on the previous page. There's more than 9 pet owners in the world, or even depending on what our population is, that's probably true too. But when I talk about the population standard deviation, we end up with not n minus 1, but n, which is important to recognize the difference between these two things. Most of the time, like I said, our calculator is going to be calculating these things, and it's definitely going to take into account the n minus 1 versus the n, basically whether it's an s or a sigma, but that's not something that you have to worry about. I think I've already talked with some of you whether or not you're in AP Psychology, in which case this is a section that's very much covered by Mr. Jensen. And if you get confused with the n minus 1 versus the n in his class, make sure to just kind of clear that up or specify. Him and I have been doing this long enough that we've encountered this issue and we've talked about it, so I don't think he would hold it against you. But just know that the sample uses n minus 1, not for really any good particular reason. Hang on, cut it out. Not for any good particular reason that we could define without advanced calculus, other than noting that n minus 1 gives us, better data values that are actually more indicative of a typical spread. Basically, the data works better when we use n minus 1 for a sample, so we do that instead. A minute detail that might be confusing, but at the same time, trivial enough for you to not lose any sleep over. Okay, that should do it. Thanks for watching, guys.